Hello and welcome. Here we have an example of dependent type of motion. As the title suggests, motion of one moving object is dependent on motion of the other. Now, in this case, a truck becomes stuck in the sand at a local beach. To help, a friend takes a 50-long rope, ties one end to her car, loops the rope around a bar at the front of the truck, and then ties the other end to a stationary tree as shown. If the car accelerates at a rate of 0.2 meters per second squared, what will be the velocity of the truck by the time it gets to the tree after it has traveled 20 feet? So what I want to do is draw the top view of the situation. Suppose this is where the tree is. Let this be a stationary point, and let this represent the rope. Let's say the rope goes all the way here, wraps around a bar in front of the truck, and then is brought all the way tied. The other end is tied to the car, to the friend's car. So let this point represent, let the bar represent a pulley, so the rope is actually sliding around the bar, which can be thought of as a pulley. Suppose I call the truck particle B and the car A. If I put the origin right here, position of B I designated as X sub B, and position of the car I designate this as X sub A. So what we want to do in these types of situations where we have a dependent motion type problem is to take advantage of the fact that length of the cable, or the rope in this case, is constant, and write an equation for the length in terms of the position variables. This equation is commonly called as the constraint equation. So length of the cable, total length L, equals to let's see, I have two pieces here and here, 2xb, so 2 times xb plus this much, which is x sub a, position of moving particle A. So this adds up to 50 feet long. Now observe that this is a position equation. By definition, if I take the time derivative of both sides, the fact that length is fixed, its derivative is 0. So for the right side of the equation, I have 2 times derivative of xb, which is 2vb, plus derivative of xa is velocity of point A. If you like, you can use x dot to mean first derivative of position, which is actually velocity, or x double dot as the second derivative. So if I take a second derivative of L with respect to time, second derivative of constant is still 0, then 2 times derivative of VB is AB, derivative of VA is acceleration of car A. So now I have the velocity relationship and the acceleration relationship. Observe that statement of the problem says the car accelerates at a rate of 0.2 meters per second. Therefore, acceleration of A is known as 0.2 meters per second. If you like, you can call this x double dot A. Both notations are used, and you see what they represent. So I can plug this into that equation, and solve for acceleration of B, or if you wish, call it x double dot B, which is actually acceleration of the truck B, and that equals to, let's see, minus 1/2 of 0.2, or simply minus 0.1 meters per second squared, not per second, but meters per second squared, since this is acceleration. So at this point, we have acceleration of the truck. The question is, what is its velocity after it's traveled for 20 feet? Note that we are looking for an equation where velocity is desired, acceleration is known, distance traveled is known. If you recall equations of rectilinear motion for constant acceleration, we had this equation, v final squared equals to v original squared plus 2 times acceleration times x final minus x initial, or x original, whichever you want to call it. And observe that I'm writing this equation for the truck B. Okay, I use acceleration of car A to find acceleration of the truck B. Well, initially truck was at rest, so this is 0, then I can write v final squared equals to 2 times acceleration of car B, which is minus 0.1, times final position of the truck after it's traveled for 20 feet will be at origin, so x sub f is 0. Initial position is 20, therefore taking a calculator, you can figure this out, take square root of it, and report final velocity as 2 feet per second. This shows you an example of dependent type of motion. So basic procedure in these types of situations is to take advantage of the constant length of the cable or the rope and write it in terms of the position variables. Then you can take successive derivatives and come up with relations for velocity and acceleration. Thanks for watching.